I have a bunch of announcements. There's homework 4 that's due on Thursday, that's day after tomorrow. As usual, it's due midnight. The important thing to remember is this time we're using GradeScope for submission because it makes grading less difficult. I think grades make grading easy. So please allow yourself some time to get adjusted to the new system. It's entirely possible that something breaks down at the last minute. So just familiarize yourself with GradeScope and don't put off submission till the last minute. Have people started the homework? Is it done? Is it easy? Any thoughts? Any questions? More importantly. Yeah.
I have two. One is to determine if something is pack learnable or not. Is that the same as measuring the size of H, whether with the VC dimension or the?
Yes. So yes, the short answer is to determine whether something is pack learnable or not. All you need to do is count the number of functions in the hypothesis space, or if it's an infinite hypothesis space, measure the VC dimension or determine the VC dimension. In fact, I think this question came up in my office hours also, so I should probably just mention this. One way of, if you think about it, in class we characterize problems into we categorize problems into 4 groups along 2 dimensions. Which is, so we have consistent learners and agnostic, and we have finite hypothesis space and infinite. In each of these cells, we had a different theorem, all of which are called Occam's razor, and the bounds are different between consistent and agnostic. In each case, we have some theorem of the form. If you have these many examples, then with high probability we can get a classifier that is that has low error. But in all cases, the result looks something like, actually let's call this case A and case B. In case A, the number of examples looks something like some function 1 over epsilon or epsilon square. I'm not going to write that. So it's polynomial in 1 over epsilon, 1 over delta, and size of h. It is some expression that we derived. And in case B, we didn't derive it, but essentially we get result. I showed you result that looks like polynomial in 1 over epsilon, 1 over delta, and we see. Oh, sorry, it's not size of h, but it's log size of h. Here it's VC of h, right? So in case A, in any problem of type A, we said, we showed that the number of examples needed for the thing to be pack learnable is polynomial in 1 over epsilon, 1 over delta, and log of the size of the hypothesis space. Remember that in the definition of pack, you need the number of examples to be polynomial in 1 over epsilon, 1 over delta, the size of the hypothesis space, and the dimensionality. So the dimensionality is missing there, but often the size of the hypothesis space includes the dimensionality. So what you need to do is to count the number of hypotheses and see if log of that is polynomial in the dimensionality. If log of that is polynomial in the dimensionality, in all examples of type A or all problems of type A, we have pack learnable. Similarly, in problems of type B, what you need to do is to determine if the VC dimension is polynomial in the dimensionality. If VC dimension is polynomial in the dimensionality, that expression in M is polynomial in 1 over epsilon, 1 over delta, and the dimensionality, so we're good. So the short answer to your question was, in all examples of this type, you need to calculate not just the size of the hypothesis, but log size of the hypothesis. In all examples of this type, we need to calculate the VC dimension of n. What was the second question?
I have to follow up with what.
Okay.
So we had two different theories in the two different cases for A, right?
Yes.
And we should use the one based on whether the learner should be consistent?
Yes. Yes. In each case, right? In each of these cases, you have a different buffer. Because we have a consistent, an Occam's razor for consistent learners and Occam's razor for agnostic learners. If you actually look at the expressions, you will find that in both cases, here and here, this number is more than this. So if you give up the assumption of consistency, you have to pay more in the form of number of examples. So if you know that it's consistent, then you get a tighter bound.
The second question was about the structure of the depth 2 binary decision tree.
Yes.
I was wondering if you could just discuss what it means to be structurally unique, or
Is structurally different.
Yeah.
Yes. Is there like an underlying question there, or do you just want me to discuss it?
I guess I'm wondering if it depends on the labels of the leaves, or if it's just the features that are chosen.
It does depend on the labels of the leaves. So, because I thought that, okay, your question is much easier than what I had anticipated. I'm glad I asked my follow-up. So there's a slightly more difficult question that I'll get to in a minute, but the short answer to your question is yes. Because if you change the labels of the leaves, you get a different function. Right? If you get a different function, then you get, definitely, it's a number of functionally different. If two trees are functionally different, they are trivially structurally different.
Oh.
So yes. The more complicated question involves, would you count mirror images of trees as structurally different? So I'll draw two trees, and so you can have, I don't even remember what the features are anymore, so I'm just going to assume x1 and x2. So you have x1, let me use red visible. So you have x1, let's say you have x2, 3, and let's say you have 0, 1, 0, 1, and let's say here this is, we say that everything here should be the same label, right? Yes. Same feature, yes. So take this tree, and let's say I have another tree which is x1, 2, 1, 0. And just mirror it. So if you put a mirror here, these two things are the same. Are these two structurally different or not? Now, depends on how you feel about it. I would like you to explain in your answer which of these two you choose, because I realize that we didn't specify this in the question, and different people can be correct. You get different numbers which are essentially in agreement with each other, and it's orthogonal to what I want you to think about. So just make a commitment to whether you think these two are different or not, and your answer should be consistent with your assumption. Other questions? And that only makes my PA's life harder, but better to make 3 people's life harder than I famous last words. Any other questions? So if you haven't started with the homework, after class might be a good time to start. Also, if there are questions, please come to office hours, because we've had interesting discussions about VC dimension and such things in my office hours and the GA's office hours. So we still have 2 more office hours left, mine and Amy's, before your submission. Another announcement is about project. Intermediate report is due by next Tuesday. I think November 12th is Tuesday, so let's go with that. If this is just a checkpoint to kind of make sure that you're doing something with the project and not leaving it off to the end. For the competitive project, you should have submitted at least 2 different runs to Kaggle. I understand there may be some bugs, and I'll look into it tonight. And you should also have, in addition to having it to submissions on Kaggle, you should also have a report on canvas that details, that explains what you did, what's going on, what your plan is, how, and just you don't need to make a commitment, but make some plans for what kinds of algorithms you're going to try out. Take a look at the class syllabus and see what's coming up. We've already covered enough that you can have like 4 or 5 different algorithms, but just take a look ahead. For the exploratory project, you need to have made some progress beyond we've got the data. Something involving machine learning. It could be something trivial. It could be something like we've got the data, here's some analysis, here's some difficulty of the problem. I ran some algorithm from the homework on the data, and this is what I get, and here's what I'm planning to do for the rest of the semester. I think there are not too many of you doing the exploratory project, maybe like 5 or 6 teams, and I have already met with at least 2 or 3 of those. If you would like to meet with me, send me an email. I'll try to find some time. Any questions? One thing that some of you forgot for the project proposal thing for the competitive project is you forgot to make your submission on Kaggle. You just gave me a file with your Kaggle ID, and I go there and I find nothing with your name on it. That means you lose some points. The proposal was smaller. This one's slightly bigger. This one's worth 20 points. 2 more announcements. One of them is more logistical. We had to move the TARs for the Monday TA to a new room. This is, I think, just around the corner or across the hallway from the old room. So the class website will be updated with this. There should be an announcement on Canvas also. So just the other one stays where it was. And my office hours tends to be in my office unless there are so many people that we need to go to one of the conference rooms. And one more announcement, there's another fun talk. This is the second talk of the AI lecture series for this year. Mari Ostendorf from University of Washington will be visiting us this Friday actually. And she's going to talk about speech or understanding speech. Mari has done really cool work on how to build models for understanding speech. This is in this building in the 3rd floor. There will be some form of refreshment. I'm not sure if it's pizza or something at 1:30 just before the talk. Just to kind of make this interesting, I think last year or a couple of years ago, Mari led a team that won the first Alexa prize for conversational chatbots. And maybe we should talk about that. Any questions, any logistical things you want to get out of the way before we go back into SVMs? Right, let's jump into where we were. In the last lecture, we kind of started looking at support vector machines. Today, we're going to look at the details of it. We're going to develop the optimization objective for support vector machines, and hopefully, at least hopefully, get started with how to solve that optimization problem. But the story of SVM starts off like this. From pack learning, we know that lower VC dimension improves generalization. That's good. And the other thing is Vapnik's theorem said for linear classifiers, if you for 2 linear classifiers that are in the same space, in the same dimensionality, you should pick the one that has the larger margin because the larger margin has a lower VC dimension. So VC dimension is inversely proportional to the square of the margin. So this gives you a learning criterion, or at least conceptually this gives you a criterion for selecting selecting one classifier if both of them are equally good. Pick the one that has a larger margin. The larger margin gives you lower VC dimension. Lower VC dimension gives you better generalization. So the classifier with the larger margin has better generalization, or at least theoretically. So the whole agenda of support vector machines is to find classifiers that have large margins with this theory in mind. And in fact, this applies not just to linear classifiers. The idea of max margin classification or max margin learning goes beyond that, and it gives you a general criterion for learning for any classifiers, not beyond linear. So what we're going to do now is build up an optimization problem that guarantees us that we will find a classifier that has a margin that's as large as possible. To do that, we need to recollect two things from what we saw with linear classifiers. The first one is, of course, the definition of the margin. The margin is, remember, the distance of the point that's closest to a hyperplane. So if you have, I'm showing you this picture in 2 dimensions, but you can imagine something like this in higher dimensions if you want. Yes?
Just a quick question. On the previous slide, you said that lowering the VC dimension or increasing the margin lowers the VC dimension.
Mm-hmm.
That doesn't really click with me. I don't understand like how those two are related.
Which one? The first one or the second one?
Didn't you say lowering the VC or increasing the margin lowers the VC dimension?
Yes. So that was this theorem that we saw, and I'm not going to go into too much details, but intuitively, if you have these two hyperplanes here, so let's say you have these two same data set, but you have to pick between two classifiers. If you have to pick between H1 and H2, the intuition says H2 is better because H2 has a larger margin of safety for a future example. It's possible that a future example for a future positive example might be close enough to the other positives that it might accidentally fall on the wrong side. So larger margin gives you higher VC, better generalization. How do you capture this intuition using the language of VC dimensions? Thankfully, we don't have to worry about it. The Vapnik's intuition was that instead of thinking of classifiers as just classifiers, let's group all classifiers of a family within a hypothesis space into ones that have the same margin. So let's say H1 is all linear classifiers that have margin gamma 1, H2 is all linear classifiers that have margin gamma 2, and so on. And if gamma 1 is more than gamma 2, the previous intuition says the entire set of functions H1 is better than the entire set of functions H2. If all of H1 and H2 separate the set of points that you have, you're better off picking H1 because of an intuition like this. Of course, here I have managed to mess up the ordering. Here what I call H2 belongs to H1. But hopefully that works. This intuition was operationalized by this theorem from Vapnik that says the VC dimension for linear classifiers is what we proved in class or what we saw in class was d plus 1, but really it's not just d plus 1, it's the minimum of r square over gamma square and d plus 1. This means if gamma decreases, VC can get large. If gamma increases, VC can get small. That's the connection. So that gives us our criterion for learning, namely, find the linear classifier that has the maximum margin. Is that?
Yeah.
So, going back to linear classifiers, so what is the margin? The margin is just the distance of a point. So there are two definitions of margin. One of them is the margin of a particular classifier. The other one is the margin of a data set. Here we are talking about the margin of a classifier because we are trying to compare different classifiers. So for this particular linear classifier, we are assuming that it perfectly separates the data. For this particular linear classifier, the margin is the distance of the closest data point to it. So we find the distance of all the points and find the one that's the closest, and the distance, we know how to measure distances of points from lines and planes, so we just apply that expression. The numerator here is the absolute value, but instead of the absolute value, we can replace it with y times w transpose x. Why? Because this data is linearly separable. So y times w transpose x is always positive. Y is either minus 1 or 1. So y w transpose x is exactly the same as the absolute value of w transpose x. because the data is linearly separate. It's always positive, so this is good. And we are assuming that this particular line separates the data. So this is the first thing I want you to recollect from our discussion on linear classifiers. The second point is slightly more subtle. Imagine that we have this equation of a line, b plus w1 x1 plus w2 x2, and it gives us a prediction. The prediction is not the value of this thing. Typically, the value of this thing is also called the score, or if you want to be more impressive sounding or technical, it's also called the functional margin. So the prediction does not depend on the score, but just the sign of it. Right? You can multiply the score by 10 or 100 or 0.1 or any positive number, the sign doesn't change. This means that we have this degree of freedom. We have this degree of freedom that we can somehow exploit, and we will. We can multiply or divide this number by any positive number. You can halve all the weights, you still get the same decision. You can multiply it by 1,000, we still get the same decision, because the only thing that matters is the sign, not the magnitude. Yes?
What does that look like geometrically when you change when you multiply it?
When you multiply it, geometrically, it's as if you're zooming in and out of the system. So this could be b plus w1 x1 plus b w2 x2. This could be something bigger, and this could be something smaller. I can't zoom out, so yes, right?
Could you use that information about the distance between a point and the line or a plane to introduce level of confidence that we...
In the prediction?
Yes.
Yes. In fact, often with support vector machines and linear classifiers and many other classification systems, the score of the classifier is often seen as a confidence. If you imagine that you have a point here and it's predicted negative versus a point here and it's predicted negative, the one that's closer to the margin or closer to the hyperplane, you can think of it as the classifier is less certain because it's closer to being wrong.
So it is.
It is.
To do that.
It is actually often done. You should be careful with how you interpret the score. We'll talk about that when we talk about logistic regression, but the short version of the warning is that it's entirely possible that the classifiers might be extremely certain and extremely wrong. And that's a side effect of how we train the model. So you have to be careful with this. This is called confidence calibration, and it's a nice little niche of machine learning where very few people work on because it's very difficult. Okay, so the two things I want you to think about is, first of all, the definition of the margin. The definition of the margin is it's just the distance of the closest point, and the second one is the fact that we have this 1 degree of freedom. We only care about the sign, not the magnitude, so we can multiply and divide this expression by any positive number. Okay? Now let's take what we saw and just replace everything that I just said in math. So the margin of the hyperplane is the distance of the closest point to the hyperplane. Imagine you have a collection of points, all of them labeled xi and yi. Xi's are vectors and yi's are either -1 or 1. The distance of each point from the plane, w and b, is this thing here. Y times w transpose x divided by the norm of w. And the margin is, this is wrong. It's not the max. The min. Could one of you remind me to correct this? It's the minimum distance to it's the point that is closest to the hyperplane. So it's the minimum among all points of this distance. So just to give names to ideas, we're going to call this gamma WB. Okay? So just bear in mind there's a important mistake on the slide. It's not the max, it's the min. If you put max there, the whole thing falls apart. What we want to do, let me correct this again. What we want to do is maximize this margin. We want to find the hyperplane W and B that has the maximum value of gamma among all the hyperplanes. So conceptually, you can think of learning as search over different hyperplanes. You put a hyperplane there, you compute its gamma. You put another hyperplane, you compute its gamma. You try out all the infinite possible hyperplanes, you compute all their gammas, and you find the one that has the maximum value, and you declare that's the best because, of Wappling. Right? So this is the agenda of the support vector machine problem. We will, of course, you can't just be putting hyperplanes and computing margins, so we need to do this more efficiently, and that's what the rest of this lecture is going to be. Is this plan clear? Yes.
So this isn't that much different from Perceptron, is it? In terms of the update that you made to the...
We haven't seen an update yet. So far, it's just this conceptual plan. We have not seen any algorithm yet. But eventually, we will find that the algorithm that we will come to is about 8 characters different from Perceptron. It's very similar. The big difference with Perceptron, and here, is in Perceptron, once the classifier stops making a mistake, we will no longer update it. It doesn't matter if it has a low margin or a high margin. It's entirely possible that the classifier might be just past the decision correct side. It might be just accidentally right. So there's nothing in the Perceptron that says maximize the margin. And whereas here we have a criterion for picking among classifiers that are all equally good. In Perceptron, if any classifier is good, we stop. Does that make sense? So
yeah, so before we do this, do we have to have classifiers that we know correctly separate the data?
For now, let's play that game. And then very soon we'll drop that assumption. So if you have a data set like this, a Perceptron might be happy to stop with this line here. SVM will not be happy because that is pretty awful in the margin sense, and it will try to find something that looks like this, because this has a larger margin. So this expression gamma WB is called the geometric margin because it normalizes this numerator by the norm of W, by the length of W. The numerator alone, this thing here, as I said, is called the functional margin, which I find very confusing because these two words are very similar, so I'll just call it the score. So I'll just call this the score of the classifier. And the reason I call it a score is for that question that came up. It's like the confidence of the decision. So here's the neat trick that we're going to pull on, and this is going to be slightly risky. So we only care about, we want to maximize this quantity, and we only care about the sign and not the magnitude. What that means is that I can divide W and B by any positive number. In fact, let me write that down. Let's say I divide everything by a number C. W1 divided by C plus W2 divided by C. So 1, 6, 2. I can do it. Which means, how will this thing change? This will change by, this will be W1 divided by C plus W2 divided by C. 1. Oh, what have I done? Okay, I changed the order. So this changes to 1 plus W2 plus C divided by W square plus W2 square. The C is common everywhere, it gets cancelled out. So dividing does not change this formula. Right? So the margin remains the same, but I can essentially divide this by any value. Okay? So then what if I, what did I do here? Something's wrong.
B divided
Oh,
by
thank you. Yes. Yes. So now I get to imagine that just for optimization purposes, I pick a C that is convenient for me. In fact, what if I pick a value of C that, let's think about the best classifier out there. This is the classifier that we want to get, the maximum margin. Let's call it W star. Imagine that we had access to W star. We don't, but it's an object that exists. Let's say I set C equals the length of W star. I don't have access to it, but I can think about it. And if I do that, at the end of optimization, what will happen? The point that is, so before we move on, does that, yes?
Can you explain what W star is?
So imagine, so I would like to find the classifier that has the maximum margin. Let's give that classifier that has the maximum margin a name. Let's call that W star. And I set C to be the length of that particular vector, the weight vector. I don't have access to it, but it's a number. It's a positive number, which means everything that I said about dividing and multiplying by positive number holds. So which means I can set C to be equal to that. Now, what will happen when I set C equals W star to this quantity? In particular, what will happen to the closest one? Why? Why? Can you tell me? Actually, what will happen to the numerator of that thing? Yes. Your answer is right, but can you tell me what? So the answer is, when C equals W star, the numerator becomes 1. At optimum. Only at optimum. Let's work it out. At optimum, W1, the weights that I learn will be equal to W star, right? Because those are the weights that I have declared I want to find, and let's assume that we have a optimization system that finds us the best weights. At optimum, W equals W star. So this expression will be, I'm going to erase this because I need space. So this expression will be W1 star. I have already divided by the length of W star, right? Divided by the length of W star, which is C, right? Times x1 plus W2 star divided by the length of W2 plus B divided by the length of W star. Thank you. Let me zoom in. There is a technical detail here. I'm putting B into the weights here, but let's not worry about that. But essentially, times x2. Essentially, what we have here is a unit vector, right? So this is a unit, this and this. I'm following the trick of putting B into the W star as well. All of these form a unit vector, which means the closest one of those will be equal to 1. Let me restate this. Instead of going through this whole pain, let me restate it in a different way. I'm free to choose any C I want. What if I choose the value of C such that for the closest point, and only for the closest point, the numerator of this expression becomes 1. I can pick any C I want. In hindsight, let's say I run the whole process, get the weight vector, and then find the C that makes this expression, just the numerator, equal to 1. I mean, there is a certain choice of C that does that, right? And remember, choosing a positive numbers of C, a positive value of C, does not change the function that I have. It only changes how much I have zoomed in and out. So I could have chosen any C I want, and what I will do is I will choose a certain scaling factor C that makes this numerator equal to 1. Yes?
I'm not quite sure, but why do you want to do that?
I'll tell you why I want to do that, because it's going to make optimization so much easier. It's going to give us a problem that's actually easy to solve. Okay, it's easier to solve because it's only one lecture of work rather than a lifetime. But this is a rather nifty trick, and it's something that you need to take some time for it to sink in. I mean, if you don't get it now, I want you to go back and think about this and try to reconstruct the argument. Rather than just taking me on faith, try to reconstruct it and come back to the question. The intuition is the following. I get to pick, I only care about the sign, which means I can zoom in or out however I want. Okay? What if I get to choose the zoom, which is essentially the C, to be that positive number that makes the numerator of this expression for the closest point and only for the closest point equal to 1. I choose that zoom. I don't actually have to choose it. I assume that's the value of zoom that I'm working with. And once I do that, what I get is that the margin, using the weights that I have and the zoom level that I'm working with, the margin is 1 over the norm of W. You had a question?
What happened to the C that we had on the bottom? Were we dividing everyone?
Yes, and this is why I didn't want to. This is why I was kind of sketchy on the last slide. This is only true for the W star. This is only at the optimum. I'm assuming that these W's are the optimums, at which point W optimum will contain the C. Because it's the weight that we learn.
So that's really W1 star.
Yes, yes, yes. At optimum, the numerator will be equal to 1. Only at optimum. Yeah, I first made a version of this with W1 star, but that looks so bad because you have some superscript with stars and squares, and it just looked ugly. So maybe I should not have done that. But essentially here all the W's are the optimums. At optimum, I want the numerator of this thing to be equal to 1. What does it mean to say the numerator is equal to 1? It means the margin is not this expression that's crossed out, but it's just 1 over the norm of W. Right? Because the numerator is equal to 1. So the margin is just 1 over norm of W because I am defining the numerator used for only the closest point. For other points, it might be more. But for the closest point, the distance is just 1 over the norm of W. Any questions? Any concerns? This is often the point that most people feel the most uncomfortable about. Yeah.
So why wouldn't this be true for any other classifier with the right scaling?
The reason it won't be true for another classifier is it's entirely. I'm going to erase all the lines, and now that I look at them, they make no sense. So imagine that another classifier found, another learning algorithm found a classifier that looked like this. So something like this. There, it's not just scaling that's changed. There's also some rotation. Right? So now the margin is actually pretty small. It's entirely possible that the perceptron algorithm will find this line. In SVM, what we want is to find the line in the middle. And this is the definition of the SVM. Any algorithm that actually finds that line is actually an SVM. SVM is not an algorithm, but it's a conceptual way of defining a learning algorithm. Whereas the perceptron might actually just find this green line and stop. So there's no reason that the perceptron maximizes the margin.
Right. But
and the reason for that is because there's nothing in the perceptron algorithm. If you think about the update rule, there's nothing in the perceptron algorithm, in the update rule, that says after finding a classifier that correctly classifies the data, make any change. There's no reason to make a change because updates happen only if there's a mistake.
Right. So how does where does the scaling and zooming fit in all this?
In the perceptron,
No, in the SVM.
it fits in entirely in the theory of it. In the actual algorithm that you implement, it's going to disappear. So we go through this pain to make the next step easy.
So I'm a little bit confused because say that you're given a green line.
Oh, let me just draw that again.
Yeah.
Yeah.
And you want to somehow turn it into the blue one. Like
Okay.
that's the goal, right? Or
Keep going. I don't know where your question's heading. So
it's like, okay, so I have some classifier that's good classifier.
Yes.
And I want to determine whether or not it's the best one.
okay.
So say I'm given that classifier,
Right.
and then I say, is this acceptable or not? So it's almost like you're trying to,
Rotate the green line to be the blue line.
yeah. Or
So let me. You're thinking algorithmically. You're thinking, what should I do to fix it? At this point, I have not yet gotten to the algorithmic level. I'm just describing this declaratively. I'm just describing a state of affairs that is preferable. All I'm saying is that the blue line is preferable, and the blue line has this property of, this having this degree of freedom. Other lines don't have it, and I can use that.
so then my question is, why don't other lines have that property?
Oh, other lines actually have a similar property, but you don't get to. Yeah, of course, in the green line also I can zoom in,
Yeah.
right? But at the same level of zoom, irrespective of what the zoom is, the blue line is better than the green. So at this level of zoom, let's say the margin for the green line was some number, and the margin for the blue line was some other number. It seems like at this level, blue is better than green. Now maybe it's entirely possible by changing the zoom, green becomes better. But it's not true because when you zoom in, both blue and green change, and blue still remains better. The fact that blue is the better line, has a larger margin, is independent of what level of zoom you are at.
Oh, so the one is just a normalization.
That's right. So that's right. So the one is just a way to fix the zoom level, so that we can pick the optimization. The optimization becomes easier. Yes.
Yeah, it sounds like the SVM always provides a better solution than the perceptron algorithm. Is there a reason to use the perceptron instead of SVM?
So this is a good question. The question, those of you who didn't hear it, is it seems like SVM is always better than perceptron. Is there any reason to use perceptron? You should not use the perceptron first of all. You should use the average perceptron. Now it turns out average perceptron. Remember, perceptron comes with no guarantee, no VC, no generalization guarantee. Average perceptron is supposed to mimic the voted perceptron, which I didn't give you a theorem, but comes with a theorem of generalization. So the average perceptron is supposed to simulate the voted perceptron. In practice, I have found that SVM, average perceptron, logistic regression, they are all roughly equivalent. And my choice of which one I would use is decided entirely by which one I have efficient code for. Because frankly, they're all roughly all the same. So the answer to that question is use the one for which you have better code. And the important criterion is each of these algorithms come with their own hyperparameters. The statement that I said is only true for the best choice of hyperparameters. So of course you need to do cross-validation, you need to find the best hyperparameters. And given that, it's really not going to make much of a difference. And in fact, I'm hoping that you will find that I'm right also for your project by comparing average perceptron versus SVM. And hopefully you will find that this is the same. Okay, so long story short, we want to maximize, same mistake. we want to maximize the margin. In other words, we want to find a hyperplane that has the maximum value of gamma WB. But we can change the normalization factor so that the closest point, namely the I here that minimizes this expression, has numerator equal to 1. So we want to find maximum gamma WB such that 1 over the norm of W is equivalent to saying I want to maximize, find a W that has maximum 1 over the norm of W. But it's not maximum 1 over norm of W. It's maximize that quantity provided the numerator for the closest point is equal to 1. In other words, the closest point should have a score of 1. In other words, all points should have a score of at least 1. Right? So, finding setting the functional margin of the closest point to be 1, I want to find the W that maximizes 1 over norm of W. This is going to give us the objective. Yes?
Could you please flesh out that idea about having the number 1 instead of 2?
2 is also fine. Pick a number, a constant.
Why do we want to do that? I mean, you said it because it will make our life easier during the optimization, but why will it make our life easier during the optimization?
Literally the next slide.
Okay.
Literally the next slide. So actually, let me just give you a preview because I can see you're eager. So originally, I wanted to say that I wanted to maximize gamma WB. I'm going to drop the B because it's just annoying and I'll forget it. So you know how to get rid of the B by just making it a feature. So that's what we're going to do. So I want to find W that maximizes this one. This is exactly the same as saying maximize for W. The definition of this quantity gamma W is the minimum over all examples of Y W transpose X divided by the norm of W. Instead of doing this, what if I say, suppose I only consider those W's such that the numerator here is equal to some constant, 1. 1 is a convenient number because you can forget it. You don't have to keep track of it when you multiply. So instead I'm going to say, I want to find the maximum for W such that of 1 over the norm of W if of Y W transpose X equals 1 over W. Such that the closest point has Y W transpose X equals 1. Or equivalently, I'm going to just continue with this if side. If min over I Y W transpose X, I is an I, equals 1. Or equivalently, if yi W transpose xi is greater than or equal to 1 for all I wanted to maximize this quantity such that this condition is true.
And you're saying that optimization is easier instead of the one above?
It's much easier than this optimization because it's a well understood family of convex optimization problems. It's something that convex optimization people have been studying for, I don't know.
Now it makes sense. I was waiting for that argument.
Yes.
So this is a convex optimization, whereas the one above is not a convex.
It turns out it's also convex, it's just hiding because they are the same problem.
Yeah.
They are the same problem. This is one that is more computationally easy. Yes?
Unless I'm missing something, the maximum margin is independent of the bias term.
Yes and no. The bias term adds a tiny bit, but it doesn't make a difference. The margin is technically defined to be, if you unroll the bias term, it's the y times w transpose x plus b divided by the norm of w.
Which is equal to 1. So the maximum margin is inverse proportional to the norm of W.
Oh, it's actually norm of w plus b squared. if you had the bias term run, if you carried the bias term. You will have a plus b square everywhere. And that's just going to be there's a way of proving that it doesn't matter in the thing that in what we're going to do, but you will have a plus b square in actually, let me just make sure this is right. You won't have a plus b square here. Yes, actually you will. You'll have a plus b square, you'll have plus b here, and so on. So there will be a b that's tagged along everywhere. The difference will be in your distance, that in the formula that talks about the distance of a line from a hyperplane. Usually you don't put a b here or a b square here. So where did this come from? There is some subtle argument that proves that these two are equivalent from the maximum margin point of view. Maximizing this will give you the maximum for that. And I'm not going to go into the details, and if you had not brought up the question, I would have completely brushed it under the carpet. But there is a way of proving that these two will give you the same maximizing hyperplane. So it's better to solve this because it gives you control over B. Or if you do not optimize, so the maximization will be max over W comma B. So if you do not control the B term, you will, if entirely possible, you can get an arbitrarily large term there that reduces the quality of the classified eventually. But that's a detail that I don't want to get into. Okay, so essentially I've given away the story, so I'm going to redo it now.
Yeah, I have a question. To me, it seems that this SVM and the way we are going to do it, it will work fine if L2 norm of a vector is representative for a distance between two points or points in the line. But are there applications or use cases when the L2 norm is not representative and hence SVM fails?
There are applications where the L2 norm is not representative, and in fact, it's not very common, but there is a whole line of work on L1, using L1, and it has interesting properties, and we'll come back to that question maybe at the end of this lecture because it actually is a very cool idea.
And SVM then still somehow works?
It's called L1 SVM.
Okay.
I mean, you can call it what you want.
Right.
This algorithm just looks like the marginal perceptron with some regularizer.
Yes, that's exactly right. Okay, so what we have is we want to maximize. So remember, I want to maximize over W. I'm going to drop the bias term throughout because if I don't drop it, I know I'll forget it. Instead, assume that the features have been extended by 1 and there's a bias feature. So we want to maximize the norm of W. That's exactly the same as minimizing, we want to maximize 1 over the norm of W, which is the same as minimizing, or not equal to, but this problem is the same as minimizing over W, the norm of W. What is the norm of W? The norm of W is simply the square root of W transpose W. So this problem is equal to saying I want to minimize this W transpose W because I don't want to keep track, remember the square root. So essentially, this is a standard thing we do in calculus where you have a square root, but square root is just a monotone function, so we don't have, it doesn't change the W that minimizes it. So instead of minimizing this problem, we're going to minimize this one. Instead of minimizing this, we're going to minimize this. But you can multiply and divide by any constant, so I'm going to have minimize square root half of W. Sorry? Okay, yes. We can multiply and divide by any positive constant, so we're going to put half there because that will prevent us from making mistakes in the future. This is just, we're going to take a derivative of this thing, and a derivative of a square is 2x. And then you'll have to carry the 2 along. Let's not do that. So we want to maximize this, but all of this is subject to the criterion that the closest point has a score of 1, which means every point has a score of at least 1. Okay, so that gives us an optimization problem. I want to minimize an objective which is W transpose W, half W transpose W, such that some constraints are satisfied. If you have not seen this kind of an optimization problem before, you can think of it as essentially a search. I'm going to search over the space of all vectors of type W, but I'm not going to search over all possible vectors. I'm going to search over only those vectors where the constraints are all true. If even one of those constraints is not true, then that particular vector W is not in my search space. It's no longer interesting to me because it does not satisfy my constraint. So, minimizing over W gives us maximizes the norm 1 over the norm of W, and this condition, the condition below, is true for every example, and in particular, equality is achieved for the ones that are closest, because those are the ones that define the margin. This problem is called the hard support vector machine, and it's not called hard because it's difficult. It's called hard because it assumes that your entire data set is separable, so it is hard separation. We won't worry about how to solve this problem right now. We'll worry about how to solve this problem later. First, I want you to understand just the specification of this problem. Any questions? Or any more questions? Because this is not the easiest thing. Yes.
So with all this predicated on having an accurate or having a series of accurate classifiers? Because you can imagine the data set is linearly separable, but incorrectly linearly separable as well.
This is all. Wait, what is incorrectly?
Because imagine you have points that are in all 4 quadrants, and there's a line that separates them in 2 different ways. One way would be correct, one way would be.
Don't call it correct and not call it better. One of them is better. You prefer one, right? There may be multiple ways of separating the same data set, and you want to impose a preference among all the classifiers that are equally good just in terms of accuracy.
So this depends on having a series of classifiers that have equal accuracy.
That are all perfect, in fact. Because remember, look at that condition there. The condition is saying every example should have y w transpose x greater than 1. Greater than 1 means greater than 0. Greater than 0 means y w transpose x is always positive, which means for a positive example, w transpose x is positive. For a negative example, w transpose x is negative. Which means this assumes your data set is linearly separable. And that's why this is completely useless. Because you never have linearly separable data. Yes.
So
Did that answer your question?
Yeah. So when you change the top term to just a 1, essentially what you're doing is just restricting the search space so that you don't have to look over as many functions, right?
Yes, that's right. And we're doing 2 things. We are restricting the search space, that's why we get this constraint. And 2, we are making the objective function that we are optimizing a function that is easier to handle. It gives us less grief. Just from a mathematical point of view. Otherwise, you would have a function that looks like this. So just to kind of step back and see where we are. So far the story goes like this. Lower VC dimension gives us better generalization. Larger margins gives you lower VC dimension. And for separable data set, we want to find the classifier that has among all classifiers that separate the data, we want to find the classifier that has the largest margin, or equivalently, among all classifiers that have satisfied this property, which is essentially saying among all classifiers that have separate the data with margin at least 1, we find the one that minimizes the norm of W, or W transpose W. These 2 statements are equivalent, and I kind of hand waved the proof just now. I built it up. Questions? There must be a problem here, right? I mean, this can't be all. So, one obvious problem came up just a few minutes ago, and can someone else tell me what it was? Have we solved everything? I mean, can you now work on any data set using this tool? Yes.
What if the data isn't linearly separable?
That's right. This is a big if. Life is not linearly separable, so we need to deal with that. What if the data is not linearly separable? That's an excellent question. Here in the hard SVM, we assume that every example has a functional margin of at least 1. And we want to maximize the margin. I keep saying maximize the margin, but that's exactly the same as minimizing W transpose W. This is a constraint optimization problem. We want to optimize some function, namely W transpose W, subject to constraints. If the data is not linearly separable, there is no set of weights that satisfy these constraints. At least one example, what's the definition of a data set that's not linearly separable? There's at least one example which, for any set of weights, will make that inequality false. If the data set is not linearly separable, that means there will be no W that satisfies all those inequalities, which means the set of W's that this minimization is operating over is the empty set. You're searching over the empty set to find a set of weights that has the minimum norm. This is not a well-defined problem, and if you want to think of it from a programming point of view, you'll get an exception. This does not compute. So you have an infeasible problem and there is no solution, and at this point we have two options. Either we can give up or fix the problem. And we have half a semester to kill, so let's try to fix the problem. In fact, the fix here is actually another really clever thing. In order to fix the problem, what we will assume is, what if we allow some examples to break into the margin? We have some data set, and what if we allow a few examples to violate that condition that all examples have to be correctly classified by the right classifier? Instead of trying to find the perfect linear separator, instead of doing that, I want to find the best linear separator that correctly classifies as many points as possible. And among the ones that it has classified, I want to find the ones, the classifier that has the largest margin. So in this picture here, so there are 2 points, the ones that are circled, that have broken into the margin for this particular hyperplane. The negative point is clearly on the wrong side. It should not even belong there, and maybe it's noise. And maybe the positive point, and let me allow it to break into the margin because that gives me a larger value. Just by essentially ignoring that point, by ignoring these 2 points, I get a linearly separable data set. Now that seems nice, right? I mean, if I can choose which points to ignore, suddenly that seems like cheating. But let's see how far we can run it. Maybe by doing that, you will get a large margin separator that will generalize better because these 2 points are outliers. If we could detect that, then life would be good. How would you do that? Well, we can just ignore those points, right? So let's see how we can do that. This is called, I'm going to just to contrast this against hard SVM, I'm going to call this a soft SVM. In fact, it's just called the support vector machine. Nobody says soft SVM, people just say SVM. So we started off with this condition that said, I want to minimize half W transpose W subject to the constraint that Y W transpose X should be greater than or equal to 1 for all examples. What does it mean to say that an example is ignored? One way of thinking about that is, instead of forcing it to be greater than 1, what if I force it to be greater than some number 1 minus something? It does not have to be more than 1, it can be more than 1 minus some smaller number. I mean, 1 minus some number. This is my best approximation of the Greek letter psi. I never learned how to write it, so I just write it as a squirrel. So I allow every example to not, that's not xi, but something like that. I don't want every example to have a functional score of 1, but I'm going to optionally let the learning algorithm figure out which examples are outliers, and instead of saying they should have a functional margin of at least 1, I want them to have a functional margin of at least 1 minus psi I. And if all the psi i's are positive, then if a data point is really inseparable, by the way, this is how psi should be written. If there's a point that's really bad on the wrong side, then let's assume that its psi I is a really big positive number. That means 1 minus psi I, this is embarrassingly bad, is a really large negative number. Why W transpose Xi has to be, it's okay if it's a negative number for that example. Any questions about the intuition? These psi i's are called slack variables. We allow examples to break into the margin by saying, instead of demanding that YW transpose X should be greater than 0, or even, in fact, greater than 1 or even greater than 0, I am allowing YW transpose X to be greater than some negative number. It could be minus 100, could be a minus a million. Yes?
So psi I is for every single point of the data set, right?
Yes.
It seems like that's not really realistic, because how do you assign that to each value?
Aha. So that's a good question. If only I knew which examples were outliers, I would give them large values of psi I, and then essentially what I'm doing is I'm saying ignore them when you're computing the margin. But how do I know which examples are outliers? And even worse, what if my learner decides that every example is an outlier and essentially throws out the data set? It could do that. Nothing so far prevents that. Which means we need some way of controlling psi. We need the size not to be large as an aggregate. Right? So before we get into how we fix that, just let's talk about the intuition. The slack variable psi I allows each example to break into the margin. If psi I is 0, we are assuming the psi i's are all positive. If psi I is 0, that means for that particular example, YW transpose X is greater than 1. That example is correctly classified, and not just that, it's either on the margin or far away from it. It's correctly classified and it's well separated. Only those examples that are problematic will have psi I less or more than 0. Because those are the only examples where the slack variable is positive. So the question is, what prevents the learner from saying, I don't like any example, I don't like this data set, let's throw out everything? There are two, yes.
It seems a little bit like a chicken and egg. I mean, you've defined a margin, assuming you've already thrown some of those guys out.
Yes.
And don't you have to figure out who the outliers are to take them away before you calculate the margin?
Or maybe together. And that's what we're going to do. It is not safe to throw out examples without actually figuring out what the margin is. And you can't compute the margin until you know which examples you've thrown out.
Exactly.
Yes. And the answer is you need to do both of these things together. Yes.
Why not moving from constrained optimization to unconstrained optimization so that you minimize the error that you make?
They will, as we will see very soon, they will end up becoming equivalent. We will move to an unconstrained problem very soon. Yes. So what we will do is we will change the optimization problem. And now let me just write the same, everything I've written up there except one new thing. So for every example, originally, we said every example should have a functional margin of at least 1. Now we're saying every example should have a functional margin of at least 1 minus psi I. That way we allow some examples to break into the margin. We also demand that every psi I should be positive. Importantly, we have changed the objective. Originally, we just were minimizing half W transpose W. Now we have added this extra term. And what it says is the sum of the size should be small. Instead of allowing the size to be as large as you want, I want to find not just the sum of the size to be small, I want the sum of the size to be as small as possible. That way, don't allow too many examples to break into the margin. Only allow those many as you need to maximize the margin. And now notice that we are also minimizing the W's and the size together. And this answers, hopefully, the question of this chicken and egg thing. I don't know how to figure out the W independent of the psi. I don't know how to figure out the psi independent of the W. Let's just do it together by adding up both of them. Let's interpret this objective. So we have this SVM objective, or rather SVM optimization problem. All optimization problems have a form minimize. You can write it as minimize. You can think maximize also. Some function over some variables such that some constraints are true. This is a general form of an optimization problem. The thing that you minimize, F, in that what I've written there, is called the objective, and the G's are called the constraints. So in the SVM objective, the objective contains two parts. The first part in the box here says, I still want to maximize the margin. I want to maximize margin, or equivalently, I want to minimize the norm of the W's, or the W transpose W. In addition, in order to account for the fact that my data might not be linearly separable, I want to minimize the slack also, because this minimization is over the sum of these things. I want to minimize the slack because I don't want all examples to violate the margin criterion. In fact, I want as few examples to violate the margin criterion as possible. That way I don't throw away examples. Finally, I get to control how I want to trade off these two things. Do I want to maximize the margin, or do I want to minimize the total slack? And the C is this trade-off parameter. It's the hyperparameter that we're going to introduce. If you set C equals 0, that means this disappears. If C equals 0, this thing disappears. If that disappears, then we are back to the, okay, what happens if it disappears? What happens when C disappears? Yes. You get the hard SVM. Do you get the hard SVM?
It just means that you don't care how many points you throw away.
Yes, it means you don't care how many points you throw away, and you still have that psi here. What that means is the optimization problem is free to choose a value of psi that's as large as possible. And in fact, if I were the optimizer, I would set psi to be infinity. Because this becomes negative infinity, at that point I don't have to work hard at all. I don't have to work to find a W, because any W works. Because for any W, W transpose X times Y is going to be better than negative infinity. So essentially problem solved. So if C equals 0, then I'm going to give up the entire data set. Ignore the entire data set and pick a random set of weights and declare learning is done. This is called overgeneralization. On the other hand, if C is a very, very large number, if C, in fact, let's pretend that C equals infinity, that means if C is a large number, I'm going to really penalize the optimization if it throws away examples. I don't want the sum of the size to be large at all. I'm going to penalize the example from throwing away the optimization system from throwing away examples, and if C is infinity, it better not throw away any examples. It better find a set of weights that perfectly classifies every single example. So we are back to hard SVM, right? So hard SVM means overfitting, because I believe my data set is perfect. I want my data set to be perfectly classified by the entire data, by the hyperplane. So we have a spectrum. If C is large, we get overfitting. If C is small, we get underfitting. And our goal is to find a C that has neither of these problems. This side, you're throwing away examples, you're throwing away all examples. On that side, you're believing all the examples and you're demanding that you need a classifier that perfectly classifies everything. Real life is neither extreme, so we need to find a C that is a sweet spot. How do we find the good value of a hyperparameter? You don't just try it out. What do you do when you try it out? You do cross-validation. You don't just try it out. I mean, that seems a little too loose. Okay, so last few minutes, just to quickly summarize what we saw just now. For the case when the data is not separable, we introduced slack variables. Slack variables are not something that was introduced just for the SVM problem. It's a general way of, in the optimization community, it's a general way of thinking about optimization problems where we don't believe all the constraints are true. So we're going to give up on some constraints and then move and penalize the optimizer if it has to give up on constraints by putting slack variables in the objective. Here specifically, we introduce one slack variable for each example, and the semantics, the meaning of the slack variable is we allow larger values, allow the margin constraint to be violated. One final thing before we wrap up for today is we have this optimization problem, and we went through this whole thing involving slack variables. It turns out that we can actually eliminate the slack variables and write the whole thing compactly, because notice that these are two inequalities. The first one, the one that I'm writing right now, can be, I'm going to move psi I to this side and yw transpose x to the other side, which means psi I is greater than equal to 1 minus psi w transpose I, and psi I is greater than 0 also. Right? It's greater than both of them, which means it's greater than the bigger of the two of them. Means psi I is greater than equal to max of 0, 1 minus psi I w transpose. I can combine these two constraints into a single constraint that looks like this. For every I, this must be true. Now what I can do is plug in this psi I into the objective, and it turns out it's correct, and I can rewrite the whole thing, just replace psi I greater than equal to max of 0, 1 minus psi I. I can plug in this expression here and get rid of all the constraints to get a single unconstrained optimization problem like you wanted that has two parts. It is minimize the sum of two things, half w transpose w plus c times the sum over every example of max of 0, 1 minus y w transpose x. Now this, it turns out, is fantastically more interpretable, and that's the first thing that we'll see on Thursday, because this has a very cool interpretation and nice extensions that will take us into this idea of minimizing loss. Once again, remember we were minimizing loss for linear regression. This is another way of revisiting the same idea, and that will give us, a nice sort of nice way to wrap up the SVM objective discussion. Are there any questions for the minute that are left? That's left.
Is that the sort of a loss function on the right?
This thing here? Yeah. This is a loss, and we've introduced this new idea called a regularizer that prefers generalization. Alright, we can stop now, and there is, don't forget your homework. I have office hours today if you want to C is a parameter that you get by
Do you want to send the file to
I might like it, but yeah.